velocity, and we're talking about the signs, whether it's positive, negative, let me write it out in words, positive or negative. So when you have a positive velocity, it means that the direction it's going in is positive. So it's proportional to the direction, or it's in the same, it has the same sign as the direction of motion. So if it's moving to the right, your velocity is positive. If it's moving to the left, your velocity is negative. Acceleration, on the other hand, is a little bit harder because acceleration doesn't just represent speeding up, it also represents slowing down, and it is not related to the direction of motion. It is actually related to force because of Newton's second law, which is force equals mass times acceleration, and since mass stays the same, the force is proportional to acceleration. So when you think about this spring and the direction the force is pulling, this is equilibrium. It means that is the point where the spring is not compressed or stretched. If it's pushed in the positive direction, what direction is the spring's force going to pull in? If the position of this card is in the positive, what direction is the force going to pull in? Negative. That means that the acceleration is also negative. So it is proportional to force. Why would that be? Because as the card is moving forward in the positive direction, it is slowing down. And that slowing down in the positive direction gives you a negative acceleration value. So I don't want you to think of acceleration as a change in velocity when you're thinking about direction. It's a lot easier to think about it as the direction of force because acceleration and force are going to have the same sign. So think about the direction of your force in your spring. When it's moving in the positive direction, the spring is stretched and therefore it's going to pull opposite to the direction of motion. Or actually opposite to the position in which the card is at in that point in time. Okay? So there are 7 questions here. I want you to think about them carefully. It takes you back to motion and forces, which is Unit 1 and Unit 2. Do the best that you can. These are pretty complex questions. So as I go around and call for answers, I'm going to have you collaborate with your group and come up with an answer together. All right, go ahead and start working. In the meantime, I am going complicated concept because we're tying in our new topic of waves into our old topic of force and motion. But let's start with problem number 1. It says, at what point is the acceleration positive? This group said F, G, and H because the slope is going up. So they said this section right here. So when we're talking about acceleration, we said that acceleration is proportional to force. So at F, this is a position right here where it's right below the equilibrium line or to the left of the equilibrium line. The spring is compressed. So what direction is that force going to be? It's going to be in the positive, right? So that means acceleration is positive. True. At G, that's right here in the middle. I'm not going to have a compression or an expansion, a stretch. So am I going to have a force there? No. My force is actually 0, so acceleration is also 0. So we're going to keep F, drop G, and then H is over here. That means that my spring is stretched. So what direction is my force this time? Negative. So if the force is negative, then the acceleration is also negative. So we want positive forces. We now know that anything above the line, the equilibrium line, is going to have a negative acceleration. Anything below the line is going to have a positive acceleration. And then same up here, negative acceleration. It's based on the position. So I got F. What else should I include in this list? You can tell. We want E and D. And the reason why is because if position is negative, acceleration is positive. And the reason why is because force is positive. Because force is positive and force is proportional to acceleration. I'm not going to test you on this, don't worry. It's just trying to get you thinking and connecting all of our units together. Okay, at which point does the cart have zero velocity but non-zero net force? Well, we've got A and E, which is the points in which it changes direction. It's going from a positive position and then it's switching and moving backward. So this is perfect because it has the most stretched or the most compressed point, so that's where there's no movement. The next one, C, at which point is the net force on the cart equal to zero? We kind of talked about this already. We know right here at the equilibrium point is when the force is zero and acceleration is zero, so that would definitely be C and G. There's no stretch and there's no compression, so the force is zero. So this is correct. Now we get to the harder ones. D is asking at which point is the acceleration, velocity, and displacement all positive? Well, here we have positive acceleration. We know anything below this line has a positive acceleration, but the position is clearly negative. Here all the positions are negative. So if I tried the top, all points are all positive. So then in this scenario, this group said H. H is going to have a positive position. Good. It's going to have a positive velocity, which is good. But we said that the acceleration is negative. So this is a scenario where none meet the criteria. And the reason is the same as the reason we got for A. It's because a positive position is going to have a negative acceleration. They're always going to be opposite of each other because the force of the spring is going to oppose the position of that cart. So this is our reasoning for part D. Okay, part E, at which point or points is the acceleration non-zero and opposite the sign of the position? So this group said A, B, D, E, F, and H. The only points that didn't work are C and G, the equilibrium points. And this is correct. The reason why is because a negative displacement, the spring is compressed, so it pushes in the positive. A positive displacement is stretched and pulls in the negative. And there's only 2 points where the acceleration is zero, and that would be at equilibrium. So this matches our idea of position and acceleration being opposite of each other. And then last but not least, we got at which point or points is the velocity non-zero and opposite in sign to the acceleration? This group said B and D. So B and D are here. The velocity is definitely non-zero. Here the velocity is, negative. Here the velocity is negative. but it also needs to be opposite the acceleration. So this actually meets the criteria because I've got a positive acceleration here. So this one's good. But I've got a negative acceleration here, and so B would not work. D is good. The reason why we know is because the velocity is the tangent line and has a negative slope. Are there any other points where we have the same velocity and the same acceleration? Did anyone get another point? Thomas? H, good. H has a negative acceleration and a positive velocity. Oh, they're supposed to be opposite, right? Yeah. Yep, perfect. So D and H would be your answers. You want the slope, tangent slope, same direction as acceleration or force.